the log, I'm trying to find it, there aren't very many easy ones on here. Okay, how about just log base 3 of 27? So this is saying, how many factors of 3 do you need to get 27? Well, how many factors do you need? It's 3 times 3 times 3. So you need 3 factors of 3. The log base 3 of 27 is 3. In exponential form, we would say you need 3 factors of 3 and you'll get 27. Okay, let's look at some that are a little bit trickier than that, using some of our other exponent rules. Okay, how about this one? Log base 36 of 6. How many factors of 36 do you need to get 6? In other words, 36 to what exponent will equal 6, right? That's what this really represents. This logarithmic expression represents an exponent. A logarithm represents an exponent. So this is what we're really finding here. 36 to some exponent equals 6. Well, can you think what that exponent needs to be? Isn't it the square root of 36 is 6? How do we do square roots with exponents? A square root is an exponent of a half. So this logarithm then, the value of it would be 1/2, because 36 to the 1/2 is 6, right? 36 to the 1/2 is 6. So for now, that's how we evaluate a logarithm, is we think, what would that exponent be? Let's look at another one. You know what? Let's just kind of not worry so much about evaluating it. There's going to be some of these where, well, here's a good one. Log base 4 of 1/16. What would the numerical value of that be? Well, let's think. 4 is my base. I don't know what my exponent should be, but I know I'm supposed to get an answer of 1/16. So when we evaluate this logarithm, I'm thinking, if my base is 4, what does my exponent need to be if I'm going to get 1/16 as my answer? Well, geez, isn't 16 just 4 squared? And since that's in the denominator, couldn't I write that as 4 to the -2? So what exponent do you need on 4 to get 1/16? You need -2. 4 to the -2 is 1/16. Now, I know you might be a little bit shaky on that. That's a little bit tricky there. We'll practice that more later. It's okay if you don't feel totally confident with it yet. I just want you to get used to the fact that when we evaluate these logs, we're trying to find what the exponent is. And you'll see some other expressions that might look really crazy, like this one. Okay, you'll notice that I went ahead and wrote out this whole equation. What you're going to be asked to do on a problem like this, looks like, oh, okay. What you're going to be asked to do with something like this for now is to just write it as an exponential. So it's already been evaluated. If we are just asked to write this as an exponential, then we would just say, okay, the base of the log is 4, so the base of my power is 4. The exponent, what's the exponent? Well, doesn't the log equal the exponent, right? The value of the logarithm is the exponent, because a log is, equals means is, an exponent. So that 4/3 is the exponent. And what's the power? Which is the answer to this. The power is always what we're taking the log of, which in this case is 4 times the cube root of 4. So on one like this, where the directions are just write this as an exponential equation, we didn't have to do any math there. It's just realizing that this expression and this one are equivalent to each other. And they mean the same thing. Now I'm going to look at some special logs here. These are actually the easiest kind. Let's say I have, you know what, I'm going to pause for just a second. I'm going to make sure I look at something and get it right. Okay, so there are two bases or types of logs that are used more often than others. Okay? Any positive number can be the base of a logarithm. Okay, I'm going to say it again. The base of a logarithm has to be a positive number. Any positive number can be the base of a logarithm. But there's two bases that you use more than any others. Okay, and one of those is when our base is the number 10. Okay, so let's look at some base 10 logs. The log base 10 of 10. So that means if 10 is your base, what exponent gives you an answer of 10? Well, 1. 10 to the first is 1. By the way, let's point out that when your base and your power are the same, your exponent is always 1. Log base 3 of 3 is 1. Log base 9 of 9 is 1. Log base 30 of 30 is 1. You got it. How about log base 10 of 100? Well, 10 squared is 100. How about log base 10 of 1,000? Well, 10 to the third is 1,000. These powers of 10, 10, 1,000, 10, 100, 1,000, 10,000, 100,000, these are very useful numbers in our decimal system, right? We talk about powers of 10 a lot. We call them orders of magnitude. We use them in scientific notation. So these powers of 10 are very commonly used, and so a base 10 log is really common. And in fact, since a base 10 log is really common, we call base 10 logs common logarithms. I'll just write common logs. A base 10 log is called a common log. And here's the thing, since they're common logs, then we just save ourselves the trouble and say, you know what, if your base is 10, you don't even need to write the base. So if I write log of 10,000 and I don't put a base there, you know what that base is. Anytime your base is missing, there's only one number it can be, and that's a 10. So when we see log of 10,000 and there's no base, that means I'm using base 10. Well, geez, if your base is 10, what exponent do you need to get 10,000? Don't we just count the zeros, right? 1, 2, 3, 4. So that logarithm is 4. Okay, so that's common logs, which always have a base of 10, and we don't even write the base in there. All right, there's another really common base, and this one is even more common than base 10, which like, why don't we call that common log? Well, I don't know. My line is always, I wasn't invited to that meeting. But anyways, this is logs that have a base that is this weird number that we call E. E is called Euclid's number, named after a Swiss mathematician named Leonard Euclid. One of the most famous mathematicians of all time. He wrote your geometry textbook. He's the one that wrote all the geometry stuff. Okay, any plane geometry, and even all the plane geometry, which is what you do in high school, is all Euclid almost. Okay, what is this number E? First of all, it's an irrational number, like pi. It goes on forever, never repeats, never terminates, goes on forever and never terminates at the same thing, but whatever, you get my point. It's an irrational number like pi. Now we know where pi comes from. You take the circumference of a circle, you divide it by its diameter, you always get 3.14159, blah, 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 right? Always the same ratio. It's a really nice pretty definition for pi. So what is E then? Well, it's an awesome number. It's an even more naturally useful constant than pi. Like E is a more useful number in the world of mathematics than pi is. I'm saying that. So why do we have pi day? We don't have E day. Well, because you don't get introduced to E until now, okay? Whereas pi, you learned about a long time ago. Everybody knows what pi is. It's got this nice, neat definition that comes from geometry. So how do we define E? Well, it's not quite as nice. It kind of is, if you think about compound interest, if you put $1 in the bank, and let's say your bank gives you 100% interest, but instead of compounding that interest like every year, they don't compound it every year. We've done compound interest in Algebra 1. They don't even compound the interest every month. They don't even compound it every week, or every day, or every hour, or every minute, or every second, or every millisecond. Say they're constantly recalculating that interest. It's 100% interest rate, but we're breaking that down into infinitely many little interest calculations. And we let that $1 go till the end of the year. At the end of that year, you will have exactly E dollars. Now, I know I probably lost you there a little bit, which is okay. Don't worry about that. Let me see if I can do just a little bit better. And I promise you, if we were in a classroom right now, we would be doing this big time. Okay, kind of talking about what this E thing is. But let me do it a different way here. Here's your $1. This is your 100% interest rate. 100% is a decimal, so it's 1. We're going to divide that by n for now. And I'm going to take this whole thing and raise it to the n, okay? The bigger we make n, the closer this gets to E. If n is 50, we're not really that close to E. If n